Okay, we're going to start chapter 22, which is entitled Carbonyl Alpha Substitution Reactions, okay? And that'll be the theme for the balance of the semester. We're going to talk about these kinds of reactions. So I'm on page 161 of your lecture notes. But before I begin that, if you could, I'm going to go back briefly to page 120. This was back in chapter 19. And at the very bottom, okay, of page 120, we were going over nomenclature of aldehydes and ketones and those kinds of things. And if you take notice of that, on the very bottom of page 120, I showed you two different ways to name this particular ketone. And I said that what you could do is you could take the 3 and put it right there, okay, in place of that letter N. And then when I rewrote it, I left this 3 in, but this 3 here is totally redundant. So I apologize for that mistake, and try not to make any mistakes going forward. So that was on page 120 of your chapter 19 notes. So let's go back to where we had left off just a few moments ago and take a look at these bullet points. Like I said at the introduction, this chapter deals primarily with reactions that take place at the alpha carbon of carbonyl compounds. All right, alpha carbon of carbonyl compounds. And so you already know there's a number of carbonyl compounds that would include aldehydes, ketones, esters, and there's a few others, but those are the primary ones. And what we mean by the alpha carbon is that let's just suppose you have a generic carbonyl, okay, like that, and then you have a carbon right here. Now that carbon that I just sketched could be any hybridization. You're going to see that most often it's going to be sp3, and that is the so-called alpha carbon that we will be referring to throughout this chapter, as well as chapter 23. And so what we're going to learn here primarily is that electrophiles may bond to alpha carbons, okay? And so that's going to be a way that you can build up molecules using the chemistry that we're talking about here in chapter 22, as well as chapter 23, which immediately follows. And those were the kind of reactions we were going to do in lab. I really miss being in lab, and I hope you do too. One of the things we want to do before we dig in is go back to something you had learned back in chapter 8 that applies to this particular chapter, and that's something known as keto-enol tautomerism. And there we dealt with it back in chapter 9, I think it was, when we were learning about the hydration of terminal alkynes. But here we just want to look at this in more of a general fashion. And what I mean by sample problem 2201 is that we want to be able to sketch tautomers. So this is a tautomer you're looking at, and specifically it's called a ketotautomer. And it's called a ketotautomer not just because it's a ketone, but as importantly is because we see a carbonyl with a doubly bonded oxygen. What we want to do though is resketch this in its enol form. Now you may notice that we have a symmetrical ketone here. This is acetone. So what I'm going to do is I'm going to migrate one of these 6 protons over to that oxygen, okay? But in the process, I'm going to place a double bond here. So let me go ahead and sketch that with you so that you can get a feel for what's happening. Now this is something spontaneous, okay? This is something that's happening to all ketones just as they're sitting in the flask. And so what I'm sketching here is nothing more than the enol tautomer, which means we reposition one of the, in this case, 6 hydrogens onto the oxygen, okay? So this would be the so-called enol form. I'm going to write that down. Enol tautomer. So this process is called keto-enol-tautomerism. And this helps us understand some of the chemistry associated with this process. Usually the keto tautomer is favored, and it will be throughout this chapter, but I can show you exceptions to that. So that's one reason that I have the equilibrium arrow, okay, a little bit longer on the top here because it points to the dominant tautomer. So when this concept matters, I'll bring it up, okay? Now, let's get to the basic principles that this chapter will entail. Section 22.2 entitled Reactivity of Enols, Alpha Substitution Reaction. Okay, see that word enol there? Okay, we just talked about what they are. And the reason they're called enols, and I've told you this before, is because the term ene is like alkene. Remember what alkenes were? Carbon-carbon double bonds. The term OL is like an alcohol, okay? Even though this isn't an alcohol because it's not bonded to an sp3 carbon, we use the terms OL for convenience. So this would be the enol tautomer. Now, in this chapter, we're going to have two different pathways for conducting these alpha substitution reactions. There's pathway 1, pathway 2. And they're very different, but they give very similar results. Pathway 1 is what we're going to see most of the time, is when we have basic conditions. In other words, the pH is going to be much greater than 7. Pathway 2, you might have guessed, is under acidic conditions, and here the pH of the overall system will be under 7. Okay? So let's talk about the most important one though, pathway 1, and how this works. First off, we're looking at a generic carbonyl compound here, and this is an alpha carbon, and that's an alpha hydrogen. Okay? What we have here is some strong base. Okay? And to understand that, let's go ahead and use a generic base. I'm going to just put a B here, a lone pair, put a negative charge, being mindful that it's a strong base. Okay? What's going to happen? Well, you already know that the lone pair is going to pick up a proton from the alpha carbon. Why is that? Because these protons are mildly acidic. So this pair of electrons will stay behind on the alpha carbon, and that's going to give us a resonance stabilized enolate ion. Get used to hearing that term all the time. This is called an enolate ion. What's an enolate ion? It's one in which protons have been removed by a base, okay, from an alpha carbon. So these are called enolates. Now the enolate is relatively stable as a result of resonance. And what you're going to see in this chapter, though, is rather than oxygen behaving as a nucleophile, more often you're going to see carbon behaving as a nucleophile. So this would be step 1 in a process. Okay, step 1 in a process whereby you generate an enolate. And notice again that I have the enolate inside square brackets. Okay? In other words, these square brackets are here for a reason. And that is because you're not isolating the enolate, you're generating it in situ. And then in step 2, what are you doing? Step 2, you're adding another chemical component, and this will be an electrophile. So we're going to show the carbon acting as a nucleophile towards that electrophile, displacing a leaving group. Now look what happened. What happened? What was the overall result of this? The overall result was to where you formerly had a proton, you've replaced that with some group E. And that group can be things like alkyl groups, it can be benzyl groups, other electrophiles that you could add to the alpha carbon. So we're building this molecule up. Now, pathway 2 is a little different. What we're doing here is we're going to lower the pH, okay, of an aldehyde or a ketone by having a solvent, or maybe just having a solvent that will solubilize something to lower the pH. So we're going to have acidic conditions. Okay, the pH is going to go down. And by virtue of doing that, the process that we talked about here, that is going from a keto to an enol, we're going to push that keto a little bit in the direction of the enol. Okay, so you can see at a glance, so we have an enol now. Okay, so once you've got the conditions in the right frame, then and there you can add an electrophile. Okay, So I'm not going to show you all the curved arrows for how this happens, but suffice it to say, this pair of electrons can act as a nucleophile towards that electrophilic species, and then we can move forward, and eventually, though, we get the same compound. All right? So, again, pathway 1 is more important. We'll see a little bit of pathway here in a few moments, pathway 2 in a few moments, but this part here is the dominant way of doing this reaction. Now, how is it that this happens all together? Well, the reason is because the protons, or alpha carbons, are what? They're weakly acidic. Okay, they're weakly acidic. In other words, if you are next to, which is the alpha carbon right here, if you're next to that carbonyl, that means that you have a base of sufficient strength, then you can take that proton off. But the protons on beta, gamma, delta, all the way down the line, folks, these are not acidic. Okay, so you're not going to be able to pull those off with the base, but you can these. So, what's going on? How can we affect this? Well, because of these weakly acidic protons, we just remind ourselves that weakly acidic, and the pKa can be things as like around 19 or 20, and we'll see later even as great as 10. But for the most part, they're closer to like 18, 19, 20, somewhere in there. So we're going to have a base, okay, just like I showed you up here. It's going to pick up a proton from an alpha carbon, and that's going to generate these. So what are these things called again? These are called enolates, okay? This is an enolate, and it's a resonance stabilized species that you can add an electrophile to build up molecules. So that's the general idea behind what we're doing. Let's keep moving forward on that. And let's go back, let's go to page 163, where we're going to look at a specific kind of halogenation reaction. So this is alpha halogenation, aldehydes and ketones. Now, just as the name suggests, this is alpha halogenation. What does that suggest to you? It means we're going to put a halogen, okay? And the halogens you're going to see in a moment will be things like chlorine, okay? It can be bromine, it can be iodine. We're going to put a halogen on an alpha carbon, okay? So let's look at that. Now, you may notice we don't have fluorine because you can't do it with fluorine. You have to use a different process. So, ketone, aldehyde, halogenation. So here's a general reaction. Okay. What we're looking at, this would be a generic aldehyde or ketone. And what's happening is we're going to take take that species and add an equivalent of halogen. Okay. In other words, for every 1 mole of this, you want 1 mole of that. And if you have more moles of this, you're going to end up replacing up to 3 hydrogens. So you have to be careful with your stoichiometry. So again, the halogen can be chlorine, bromine, or iodine. But notice this. Okay, what's that? This is our solvent. Okay, this is our solvent. But this is a special solvent. Why? Because this is what? This is acetic acid. Okay, and so what is acetic acid going to do? It means we have this reaction under acidic conditions, okay? So that's going to be like the pathway 2, where we do the reactions at the under acidic conditions. So let's go to these bullet points and let's talk about how this would work. Okay, first off, the conditions need to be acidic, and how do you do that? By using acetic acid, okay? So acetic acid here is very inexpensive, okay? Lots of things dissolve in it, and it guarantees that your conditions are going to be acidic. But be mindful that the substitution is only going to take place at sp3 carbons. So if we go back here and look at that carbon, it's sp3, okay? And you got to have at least 1 proton there for this to happen. So if this is sp2 or sp, all bets are off. You're not going to replace the hydrogen. It's got to be sp3. And if you're wondering about the kinetics, it's a second order reaction. Okay, so the rate of the reaction actually proceeds on the basis of the concentration of both the carbonyl compound as well as the halogen. Now I'm going to go through the mechanism with you a little bit, but let's just look at some specific examples. Okay, and what do you do? Well, you might notice here that we have this is acetophenone. This is one of those compounds that you want to commit to memory. Here you have bromine, 1 mole of each, and what is that? That's acetic acid. Okay, so do we have at least one hydrogen on the alpha carbon? We have 3. So what does that mean? That means we're going to replace one of them. So where you formerly had 3 hydrogens, you now have 2. Right? You've replaced one with a Br. And this is considered a substitution, okay? Because we have compound A, we have element B, we have product C, and we have compound D. Okay, so this is merely a substitution. You're swapping out a hydrogen for a bromine. But I'm telling you, it's very important that you have that solvent or some other solvent that guarantees acidic conditions. So what would your job be? Okay, your job would be to primarily, if this were an empty box, fill that in with the appropriate organic product. Okay, so these are very easy reactions to do. Now the next example may appear a little bit different, but if you look closely, it's pretty much the same thing we've been talking about all along. This is cyclohexanone, and does cyclohexanone have hydrogens on the alpha carbon? It's got 4, right? So it's got 4 to choose from. So chemically, all 4 of these are identical. So here we have an alpha carbon, here we have an alpha carbon. So we only need to choose one, right? We only need to choose one. And so what are these conditions? Well, we have 1 mole of chlorine for every mole of cyclohexanone. And what is that? This is hydrochloric acid. So this guarantees that we have acidic conditions, okay? So let me write that down as a reminder. So when you see HCl and H2O together, you know that's hydrochloric acid, right? So you'd have to really stir this reaction very briskly, probably seal it, okay, or put a cap on it, because this is the gas. So it looks easy on paper, not so easy to do in the lab. But what happened? You end up replacing one of the 4 equivalent hydrogens with a chlorine. So now we have 2-chlorocyclohexanone. Okay? All right. Now let's look at how that kind of reaction may proceed. What we're going to do is we're going to go through a mechanism that shows how we can do a alpha bromination. Okay? In other words, here's our alpha carbon. There's one as well. They're both equivalent. We're going to replace one of the 6 hydrogens, okay, with a bromine. Now, if you just added bromine, okay, so you had 1 mole of that and you had 1 mole of bromine, I guarantee you there's a little bit of HBr in there, okay, and that's good. Why is that good? Because that's going to guarantee that the conditions are acidic. So what you're asked to do in this problem is simply provide the curved arrows as well as the incipient formal charges. So here's a little HBr, okay, and you're going to see how important it is that we have acidic conditions so that we can maintain, okay, this mechanism all the way to the end. But step 1 would be to pick up a proton from that HBr, okay, there's just a little bit of this, okay, but this is functioning as a catalyst. Right, I'm going to write that down. Okay, this is functioning as a catalyst. So you're going to pick up a proton. Okay, so we've seen this before. Now, by virtue of that happening, we have a resonance stabilized protonated carbonyl compound, in this case a protonated acetone, and we've liberated bromide ion. Okay? Now, what did we say a little while ago? Okay, that the conditions need to be acidic. Well, by doing this, we're going to produce more of the enol. I'm going to go ahead and jump to the chase here. We're producing some more enol. The more enol you have, the more you drive the equilibrium to the product side. Okay? So what's going to happen next? The mechanism that makes sense would be for this bromide, okay, to come and remove any one of these 3 or those 3 protons. All right? And you need 3 curved arrows to show that. And what do we do by virtue of all that? We now have ourselves an enol. Now, why are enols important? Didn't we say they form spontaneously? They do, but only to a very small extent. So if we have some acid in there, we're going to produce more enol, okay? And the more enol you have, the more likely that you can conduct, and the more quickly you conduct the bromination. Now, you don't normally think of bromine being polarized because we have identical electronegativities on each side, but bear in mind that it's in a solvent, okay, some kind of solvent. It may be bouncing off the walls of the container, etc. So we have something called an induced dipole, okay? And that induced dipole briefly establishes the separation of charge. And I say, why is that important? Because when that happens, we can actually show, right, this pair of electrons acting as a nucleophile towards the positive end of this temporary induced dipole of bromine. And then we would have this bond break. Okay? Pretty magical stuff. So if we follow those two curved arrows, okay, that's going to get us to here. Right? And as you can see, this is rather stabilized. So we put the bromine in the proper spot, but what do we say this was? It's the catalyst, right? This is our catalyst. And you may remember, here's the bromide. Right, there it is. Here's that same bromide in the next step. This bromide, put the negative on there, can pick up this proton. And that becomes a lone pair, and look where we are. So where we used to have 6 hydrogens, now we have 5. We've replaced one of them with the bromine. So all of that, okay, all of that to get to here. But nonetheless, this is how the process works when you're under acidic conditions. So a person in the lab would have to monitor this reaction very carefully. Probably the bromine color starts to disappear, okay, once the color is gone, then you have a pretty good idea, okay, that it's over, so on and so forth. But it's a pretty good reaction. Okay, let's go to page 164. And you might ask yourself, well, why do we need to carry out those halogenations? What good are those compounds? Well, they're usually used as intermediates towards the synthesis of something else. So I'm going to show you another step that we can engage in. This is the treatment of an alpha-bromo ketone with a base, okay, to provide an alpha-beta unsaturated ketone. That's why we're doing this, okay? And you may recall, too, that we had another word for alpha-beta unsaturated ketone, okay? We move this down. These were called enones, okay, enones. Ene because there's a carbon-carbon double bond, one because of a carbonyl, and oftentimes that carbonyl is a ketone component. So what's going to happen, and I'll show you this in a moment, is that the alpha bromination is going to take place at the Morse substituted alpha carbon, okay, and the base is going to be pyridine. Okay, recall that pyridine can function as a solvent, but also it can function as a Lewis base, and the mechanism for the most part would be E2. So these are things that we've seen before. Now let's home in, if you will, okay, by taking a look at 2-methylcyclohexanone. Okay, here we have bromine, and here we have acetic acid. So you already know that you're going to replace one of the hydrogens with the bromine. Okay, and so specifically the hydrogen you're replacing is the one over here, all right, and not the two over there. Okay, so granted these are both alpha positions, okay, but the reason for that is, folks, is that you're going to replace the proton, or you want to call it hydrogen, on the Morse substituted alpha carbon. So this alpha carbon here has a methyl, a methylene, and a hydrogen. This alpha carbon here has 2 hydrogens and a methylene. So this is Morse substituted. That's the one that's going to get replaced. And the reason for that is because the enol that you would produce under these conditions is more stable when we have the double bond on this side versus the double bond on that side. Now that doesn't mean you don't get a little bit of substitution over here, but the dominant species will be this one, okay? All right, so what have we done? We've replaced that hydrogen from that alpha position, okay, that one there, with the bromine. Now you can isolate this compound. It's like purely isoluble. You can distill it, take an NMR of it, a melting point, boiling point, whatever you want to do. This is a compound that's very stable. But the next step is critical. This is why we're doing what we're doing this for. This is like a step 1, this is like a step 2. Y'all may remember pyridine. Let me go ahead and draw the structure in case you've forgotten it. Pyridine is an aromatic compound. Okay, it's a heterocyclic aromatic compound, like benzene, only it has the nitrogen, it has sp2 nitrogen. That gives it its Lewis-base properties. Okay, so there's pyridine. And pyridine likely can function as a solvent, so it's kind of carrying out two roles here. Let me go ahead and sketch the hydrogens. I'll sketch both of them, okay, on the beta carbon. Okay, so remember, this is alpha and this is beta. So in addition to having pyridine, what are you doing? You're heating it under reflux. Okay, and so ideally what can happen is either one of these two protons on the beta carbon can get abstracted. Okay, and the reason this isn't that hard to do, even though these aren't very acidic, is because this is going to result, okay, in conjugating this species. Okay, so here bromide's a leaving group. Now y'all remember what this is called? This is E2. Okay, this is an E2 mechanism whereby you now have a double bond between alpha and beta, and you can clearly see it over here in the product. All right. So this is now an enone, right? This is what we talked about seconds ago. This is an enone, and you can do all kinds of things with enone. You can build them up, and we'll see examples of that. So again, what did we do? We replaced a proton with bromine, okay, to make this alpha bromo species. We then added pyridine to it. We heated it, and we get this E2 product over here known as 2-methyl-2-cyclohexenone. All right, so this species now is conjugated, and it can be used for a variety of organic reactions. And this is your byproduct pyridinium hydrobromide. Okay? Now, one of your jobs is to actually figure out how all of this works. Okay? What do I mean by that? Let me have you outline a synthesis of 1-pentene 3-one from 3-pentanone. And we're going to use this up here as a model for doing that. Okay? Now, it always pays to look at the product. You say, what's the difference between here, the product we're aiming at, versus there? Well, clearly, we've lost two of these hydrogens, right? We've lost the hydrogen from an alpha carbon, and it looks like we've lost the hydrogen from a beta carbon. Now, there's no one reagent you can add to go straight from here to there. Now, if you know of one, let me know, okay? But for the most part, we can't. Now, this is symmetrical, so you could have chosen either side, but instead, this is a two-step process, and we're going to replace one of the 4 equivalent protons, okay, on 3-pentanone with a bromine. Now, can you use a chlorine? Yes, you can. Can you use an iodine? Yes, you can. But bromine's the easiest to work with in the lab, so we're going to go ahead and go with bromine. I shouldn't say it's the easiest to work in the lab, but it's certainly easier to work with than chlorine, because chlorine's a gas. Iodine's pretty easy to work with as well, but it sublimes really badly, and we sometimes suffer from solubility issues. Okay, so we're going to go with bromine and under acetic acid. Okay, now I want you to remember acetic acid's formula. Okay, it's CH3 CO2H. So this guarantees that we're going to produce a lot of enol. The more enol we produce, the more likely you're going to have an alpha bromination. So how does this work? Well, where you formerly had 2 hydrogens on this particular alpha carbon, you replace that with bromine. Okay? Sorry, I went outside the box. -1 for Dr. Southard. Okay, and over here, nothing's changed. Okay, you could have gone with either side, but I chose this side. So this is called alpha bromination. Okay, and again, this compound here is insoluble. You can distill it, purify it, and get it ready for the next step. All right, so what do we need to do last? Folks, the last step is the same as here. We need to add pyridine. So you can draw the structure of pyridine, which I had here, or you can just write the word pyridine. Okay, this is such a common organic compound that sometimes chemists just write the word pyr, P-Y-R. And I've seen just P-Y, lazy organic chemists, but P-Y-R would be sufficient. Now, that'll do it, but what do we say we really need to do? You really need to heat this. Heat it under reflux, okay, and so it doesn't take forever. But this is how you do these kinds of things, okay? This is how we convert ordinary ketones into enones using this two-step process. All right, so this is the good one. We'll come back to that later when we do more synthesis. Now I want to talk about another one, okay? And the next one's called alpha bromination of carboxylic acids. Okay, that should be the same, right? No, not really. It's a little bit different. Now remember, if you were to draw the structure of acetic acid, okay, I'm backing up a little bit. Okay, what do you notice about acetic acid? Well, does it have an alpha carbon? Sure does. Okay. Does it have alpha hydrogens? We've got 3 of them. Do we end up replacing bromines there? Can we put a bromine there? The answer is no, we don't. These aren't as reactive, okay? This is a ketone. This could have been an aldehyde or a ketone. But we don't brominate the alpha position of carboxylic acids because they're not reactive in this way. But we say, well, I want to brominate. I do want to do this. How do we do it? Well, we have to use a different set of reagents, okay? So let me show you how that would work in a general sense, and then we'll kind of go through a couple examples here in a moment. All right, so let's take a look at the general reaction, all right, and show you how this would work. It's pretty interesting stuff. So here we have a generic carboxylic acid, okay, and you can see by the OH functionality of the carbonyl, there's an alpha carbon. Now, this could be another R group, could be a real simple R group, could be aromatic. It could even, all these could even all be hydrogens if you wanted them to be, okay? But what are we looking to do? We're looking to replace a hydrogen on a carboxylic acid. Well, how do we do that? We have to use a different set of reagents. Just like before, if we want to brominate, we need bromine. But it can't do it alone. We need PBr3 for reasons you'll see in a moment. Then we're going to quench the whole thing with water. But you're going to find out the water does a little bit more than just quench. Okay? This is a pretty cool reaction. So it's not as simple as it may look on the surface. But by the same token, the overall result, okay, was to replace a bromine, okay, on a alpha carbon to make a new carboxylic acid. Now, step 1 of this process, in other words right here, this is step 1, is to take your generic carboxylic acid, bromine, and stoichiometrically you only need 1/3 of a mole of PBr3, and it's going to give you this. Okay, you say, what is that? Well, if we were to draw it out, and we can do that in a moment, you're going to see it's pretty interesting. Let me go ahead and sketch this. All right, I want to sketch that so you can see just what happened after step 1. In other words, this is step 1. In step 1, we're going to end up with this. Okay, we're going to have that R group. There's the carbon. There's that hydrogen. Okay, here's that carbonyl. But look at what we get as an intermediate. Okay, we have, let me choose green. We have the bromine there as expected, right? Yeah, that's what we wanted. But we also have a bromine here. Okay, whoa, wasn't expecting that. But we get that as an intermediate. So that's what we call an alpha bromo acid bromide. Okay, alpha bromo acid bromide. Okay, so say that real fast 3 times. Alpha bromo acid bromide. That's what that is. So that's why we need a step 2. Step 2, in this case water, is going to end up replacing, okay, that Br with an OH. So that's what happens in step 2. So step 2 is simply, if I can get my hand around this thing, step 2 is simply a hydrolysis of the alpha bromo acid bromide. Okay, so this compound here that I'm pointing at is that compound there. That's the final product. Well, some chemists got wind that this is a pretty cool thing that you could add water. What if we add something other than water? Okay, can we get different kinds of compounds? And the answer is yes, we can. Well, before we get too far into that, though, let me just show you another, in other words, the kind of thing we're looking at here. So the first thing you want to ask yourself, what kind of functional group is this? Okay, and you say, well, it's a carboxylic acid. All right. So we count the carbons: 1, 2, 3, 4, 5, 6. So it's with heptanoic acid, right? Okay, so let me do 1, 2, 3, 4, 5, 6. Yeah, right. In heptanoic acid. But the important thing here is that it's what? It's a carboxylic acid. So, folks, always do this. Always go in, find the alpha carbon, replace, and not replace, but fill in the alpha position with hydrogens. Look at the set of reagents. It's bromination, so I'm going to replace one of these hydrogens with a Br. And one of the hydrogens is going to stay intact. So, just like you expected, right? You put a Br in the alpha position. And if step 2 is water, and it is, that means you're going to put an OH there too. So let's just find out and label what happened here. Okay. So this would be basically 2-bromoheptanoic acid. So where did that bromine come from? Step 1. Came from step 1 when you added the Br2, PBr3. And where did that OH come from? From step 2, right? When you added water. Now, let's do something a little different. Okay? Rather than adding water, why don't we add the simplest alcohol there is, in this case, methanol. Okay? And let's try to figure out what that product's going to look like. All right, so what would be your first job? What do you do the first thing you see? Well, this set of reagents tells me that I'm going to do an alpha bromination. So I may as well label that alpha. Now notice there's no number in front of the bromine, so that means there's one equivalent of that, or 1 mole. There's no number here, so that means there's one equivalent, or 1 mole. That means we're going to replace one of those hydrogens with a bromine. So let's go ahead and sketch that out. Okay. So this is the R group that has a bunch of methyl groups on it all over the place. So, all right. So I'm going to put an H there. Okay, then I'm going to jump over and draw my carbonyl. Okay, and then we're going to finish it up. Who can tell me what I need to put here? Yep, you can put it on the top or bottom, doesn't matter. You know, we need a bromine there, right? Now, who can tell me what goes here? This is not water, okay? But what is water? Well, water is HOH. So in effect, we put the OH on there. So what is methanol? Methanol is CH3 OH, right? So we're going to put that part on, and we're going to end up with an ester. So water acts as a nucleophile towards the incipient brominated species, which is all tongue-tied here, okay? But here in this place, we're going to produce an ester. Okay, so that's how that works. So this is a pretty cool reaction. You could do another step here and produce a double bond there and make all kinds of products. It can even be an amine. If you want to make an amide, it can be alcohol, any kind of alcohol. It doesn't matter if it's a hindered alcohol, primary, secondary, tertiary. This reaction will work. Okay? All right. So let's see where we are. I think I might want to go a little bit further, and then I might leapfrog with you forward a little bit. Let's go a little bit further with this, okay? Because the next part's really easy to understand, and then I'm going to go fast forward to some pages in front of this in order to get this chapter on track. So the next section is entitled 22.5, Acidity of Alpha Hydrogen Atoms, Enolate Ion Formation. Now we already went over that, but we didn't go over it in detail. Here we go over much more detail, and I'm going to talk about a special way to do this. So let's go through these bullet points one by one. Okay, first of all, you may remember that the protons on alpha carbons are weakly acidic. Okay, pKa's from the ones on aldehydes are about 17, pKa's on ketones about 19, give or take. Right, so they're very weakly acidic. And then we'll see later, okay, not much later, but later, that the protons on alpha carbons are 1,3 diketones. Okay, and what those are these kinds of things. Right. In other words, let me just kind of draw a generic structure of one of those. That would be a 1,3 diketone. Those protons, because they're between two electron withdrawing groups, they're much more acidic. Okay, right? Because there's two electron withdrawing groups flanked at the alpha carbon. So when that matters, we'll talk about that in detail. Okay, because carbonyl carbon is electrophilic, hindered bases are used to extract protons from alpha carbon. That's where we're going to start going, guys. This is very unique. A common hindered and very strong base is called LDA. Okay, LDA is lithium diisopropylamide. This is its formula, and here's its structure. Right. The solvent we typically use for this is tetrahydrofuran, and the reason for that is because it stabilizes things well, plus we can get it really cold right before anything freezes. So that's what I mean by conducting the reaction at -78 dry ice acetone. So let me just show you an example of this, okay, and then try to give you an explanation for what's going on. The first thing is we have cyclohexanol, okay. We know that it has an alpha carbon, and we know that these protons, they're mildly acidic. So pK is about 20. It's going to take a really strong base. And guess what, guys? LDA is a really, really strong base. But it's also hindered. Okay, so why does that matter? It matters because you only want to remove the proton. You don't want this nitrogen to act as a nucleophile towards that carbonyl. Okay? See, if this were something small, it would go in here and react with the carbonyl, act as a nucleus. You don't want that to happen. So what's going to happen instead, you're only going to pick up the proton. Okay? And so I'm going to show you some curved arrows here for that. And by virtue of doing this, we get this enolate ion. Okay? I'm going to show it with the lithium right next to the oxygen. This is polar, very polar. It's not a covalent bond. Okay? But it shows it intact. Well, this enolate, okay, is something that you can alkylate directly. All right, but what about the byproduct? This is LDA, lithium diisopropylamide. This is diisopropylamine, simple amine. Look at its pKa. So what do we always say? Which directions reaction favor? The direction of the weaker acid. All right, so folks, there's a big difference, right, between 40 and 20. In other words, what's 40 minus 20? So this is 10 to the 20th time more weak. So this equilibrium is favored that way in its entirety. And that's another reason you have to conduct this reaction at such a low temperature, because it can get out of hand. Very, 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 very powerful reaction to the right. Now this, you don't isolate, you leave it in the solvent, and then later you'll add an electrophile to it. All right, let me just take a look at where we are. I'm going to go a little bit further with you. Let's see, page 1. Yeah. So keep that in mind. And let me just say a few more things about it, and then we'll move forward. All right. So here we have something I tried to impress upon you before. We have an enolate. And so you're not going to, once you have an enolate, you're not going to just isolate the enolate. Okay, you made an enolate. Now you want to do a reaction. Okay. So typically, though, the reactions you're going to see in this class is that the carbon will act as a nucleophile. Okay, this is common. And for the oxygen, though, to add an electrophile, this is less common. Now, chemists know, for example, if this were silicon or sulfur, there's a few other elements this would be more common. But for us, this is almost always this E here, more specifically that E, it's going to have a tendency to be carbon or halogen. So we're going to end up replacing protons on alpha carbons. We're not going to see electrophiles bond to the oxygen. Okay. All right. Okay, what I'm going to do is take a break right there, and then I'm going to fast forward a little bit and go over reactions that involve what you see on the bottom of page 165. So I'll see you a little bit later. So for now, I'm going to go ahead and stop right here.